Okay, so the first lesson, I'm calling this 1.1 because it's not officially labeled. 1.1 is numerical notation. Okay, so different ways to represent really big or really small numbers. Okay, numbers are often expressed in different notations, and understanding the meaning of the various notations is required in order to work with numbers. So our first example. I wish this example was like compared to now. This would be pretty interesting to see the debt compared to now versus 2016. We should look it up. Maybe I'm the only one interested in that. Okay, I guess it's just me. Okay, so the total debt of the United States in January 2016 was $13.6 trillion. So a number like 13.6 trillion is expressed in number word notation. So we say that verbally. Okay, so what we're going to do is we're going to write that in number notation. So ordinary notations. We're going to write it out as a number. Okay, so how many zeros? Okay, so I'm going to start by just labeling the spots of a gigantuous number. Okay, so the first number, I'm using a 0 instead of a, should I use an X? The first number, this was just like 5. What place is that? Like placeholder? Okay, I'll tell you. So this is like the ones, you know? You know what I'm going with? The ones. Okay, so the next place is the tens. There you go. So this is the tens. Okay, then the next one is the hundreds. And then there's a comma. And then this whole set, can I just be like, all this is like the thousands. And the next set is called the millions. And then after millions, you have billions. Billions. Okay, and then next we get to the trillions. Okay, so maybe just to make note, because I think I didn't make note of this last class, and I think it would have been helpful. Okay, like if I'm talking about thousands, how many zeros are there after thousands? Okay, so I have this, and there's 3 zeros after the thousands, right? Okay, so how many zeros are there after millions? 6. Okay, there's 6 placeholders. Okay, after billions, 9. 9, and then after trillion, 12. So we got to draw 12 zeros to draw, well, actually not 12, 11, because we got that 0.6. Yeah, so we're going to go 13, comma, 600 billion, and then 0, 0, 0, 0. So this was billion, million. Now I'm on thousands, right? And then my ones. Have you ever written that number before? A trillion out? Right? That is a lot of money. What? 72? Oh, interesting. So 72. That's a lot. That's so much money. I wish I had just a little triple of that. I'd take a couple of commas off of you and be happy. Okay. Okay, so this, by the way, is just number notation. We just wrote that in number notation. That right there. Okay, so you guys have heard of scientific notation. Okay, so scientific notation can be used to write really big numbers or really small numbers. She's loud. Is that distracting to anyone else but me? I feel like I need to talk loud. Okay, So when you're writing scientific notation, it's always like a number times 10 to some exponent. Okay, everybody has learned scientific notation, right? Okay. Now, sometimes when I say that out loud, sometimes people are not totally aware of how this number plays. Okay, so that a value can only between did I say that right? Can only be between 1 and 10. Okay, it has to be between 1 and 10. Okay, so okay, let's talk about the Great Wall of China. Okay, so it says the Great Wall of China in meters is 2.1 times 10 to the 7th meters. Okay, so we're going to take that, put it into numerical notation. Okay, so how would I do that? How many places? 7. So I'd go, so if it was here, right, I'd go 1, 2, 3, 4, 5, 6, 7. You guys learned that, right? Somewhere along the line. Okay, and then you fill in your little commas. I'm going to use it in a different color. Okay, well, I'll just erase it, I guess. So, now if I say that in word notation, how do I say that number? 21 million. So you would say this, so 2.1 times 10 to the 7th is the same as 21 million meters. That's a lot of meters. I really can't comprehend how big that is. Someone will ask. We'll get to the conversions later on. Okay, so here's another fact. Did you know that Earth's rotation time, it takes about 8.6 times 10 to the 4th seconds to rotate? I don't really know what it's rotating on. I don't know. Anyways, so how would we write this number? So I feel like this one, do you need to write the little swoopy things? Can you just tell me what number it is? 80. Whoops, I wrote a comment in the spot. I apparently need help. 3 zeros. So we just said 86,000. 86,000 seconds. That sounds like about a day, don't you think? There's 86,000 seconds in a day. Did you know that? All right, time needed for light to travel 1 meter. This is 1 meter. Ish. From light to go from here to here, it takes 3 times 10 to the negative 9 seconds. So I have a negative exponent this time. Okay, we're going left. So now we're talking about a really tiny number, right? Okay, so if my decimal is normally right here after the 3, right? Okay, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So my decimal is right here. How to say that number? Ooh, nice. Okay. Okay, so let's get to where. Well, let's label them, right? Okay, so what's the first? We're on the right track there. Okay, so what's this one called? You know, there's not a once. There's ones, but there's not a once. Isn't that weird? So there's a tenth. I don't know why that is. Tenths. Second one is the hundredths. Don't look at my spelling. Thousandths. What's this one? 10 thou. What's the next one? Hundredths. And what's the next one? Millions. Okay, what's the next one? 10 mils. Next one. 100 mil. So it's that one. Billions. So this would be written or said as 3 billions billionths of a second. 3 billionths. I don't say that number every day. That's kind of cool. Okay, so the size of an image sensor, I can't say that word, I just messed that up last class too. Sensor in a digital camera is measured at 5.5 times 10 to the negative 6 meters. So how would you write that? So we're moving, how many zeros to the left am I going to write? 5, right? So we'll go 1, 2, 3, 4, 5, 5, 5. Okay, so how would you say this one? Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. There you go. So 55 millionths. It's kind of interesting. Okay, what's next? Ooh, okay, so now we're going the other way. Okay, so now they're giving us the big number and we have to write it in scientific notation. Okay, so did you know the number of neurons, which I don't really even know what that is. Who knows what a neuron is? Like an atom? Brain? Little anatomical charges. That sounds good. I don't know if that's right or wrong. So there's little neurons in the brain, and there happens to be 100 trillion. What is that in scientific? Okay, so if we go back to our trillions, do you remember how many zeros was after the trillion? We have 3. So we can write it as 100 and then 9 zeros after. Should I write it that way, or should we go straight? I'll just write it that way. 100, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I do that right? 12. There we go. Okay, so now I gotta take that and write it in scientific notation. Okay, so my first number has to be between 0 and 10 was my first number. Or I mean 1 and 10, excuse me. 1. So 1 times 10, so that means I gotta move the decimal to right here. So 1, 2, 3, 4, 5, 6, 9, 10, 11, 12. We knew that. 13, 14. But you can count it out if you like. Nope, don't you know. So 1 times 10 to the 14th neurons. That's a lot of neurons. Do you think there's more neurons in some people's brains than others? It's a mass thing, right? I don't know. Who knows? Okay, velocity. So that's the speed. How fast does the Earth move around the sun? 64,700 miles per hour. So how would you rate that in scientific notation? Good. 6.4. So that number, remember, has to be between 1 and 10. Okay, how many decimals did we move it? So we went 1, 2, 3, 4, right? Then we got to go small. We got to go the other way. Okay, we got a little tiny number. The wavelength of some visible light. Some kind of visible light. I don't know. That's a sine curve. Did you know that? Wavelight is in the path of the sine curve. Yeah. Okay, so how do we write this one? 1 to the 7. 1, 2, 3, 4, 5, 6, 7. Yeah. Negative 7. Good. So remember, negative exponents mean really tiny numbers. Bigger makes bigger numbers. Okay, so you guys have heard of the metric system, I think. Or meters. Meters measures distance, how long something is. Grams. What does that measure? mass, yeah, like how much something weighs in liters, how much coffee I drink, right? Okay, so different kinds of measurements. Okay, so there's prefixes on each of those types of measurements. Okay, so this is a nice little chart. You might put that in a safe place because you might need this later on like a, yes. Okay, so we've heard of these words. Have you heard? Okay, so are these things bigger or smaller? Small. Okay, so this is small, this is smaller than that, same thing for the bottom. It sounds like music. So this is what you put the bone part? Yeah. Sounds delicious, whatever it is. Let me come do this. Okay, so Dada, Hector. Maybe I feel like that's a digital information, right? Okay, so let's see if we can do some conversions. Okay, so if they say I got 3 kilowatts, how many watts is that? Okay, so what we're going to do is we're basically given a scientific notation. Okay, so if I have a kilo, I have 3 times 10. Now I would go to my little charty. There's kilo. Right there, right? So I take that and multiply it by 10 to the third. Okay, so I take it, put it in scientific notation. So how many watts is that? 3,000. So that equals 3,000. So there are 3,000 watts in 1 kilowatt. I feel like I'm saying that weird, but yes, science class. Yeah, I hate to tell you, but usually science is where our real world mathematics appears. Okay, what about 12 milliliters? So how would I do that in scientific notation? 12, 10, so milli, good, it's up at -3. Okay, so how many liters is that? Okay, so we move that 3 paces, 3 paces to the left. So that's 0.012 liters. So, yes, so technically I'm not writing it in correct scientific notation. I understand what you're saying. So, basically, I'm taking this amount and multiplying it by 10. So, kind of like scientific notation, but really that's a proportionality. Does that make sense? Maybe I should not have said the word science. That was a wrong statement. I retract that. And scientific-ish, like notation. Good point, though. Thank you for making that point. Okay, so we are also going to do some comparisons. Okay, so comparing two numbers. What is the difference between two things? Da 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 da. Okay, so if they use the word difference, what are you going to do mathematically? Subtract. Okay, so if you ever see that, that's a whoop. Sorry, wrong. There we go. Subtract. There we go. Okay, so you're basically doing some mathematical thing. Okay, so the distance from the Earth to the Sun is 149.6 million kilometers. And from the Sun to Pluto, it's 5.9 billion kilometers. How much further away is the Sun, or from the Sun, is Pluto than Earth? So how do we say further? What are we doing? What's happening? What are we going to do mathematically? Difference. Okay, so difference means what mathematical operation? Subtraction. Okay, so we got to take the bigger one and subtract the smaller one. So which one is the bigger one? This one, right? Okay, so is it easier to just write the number and then subtract it? Like write it out in numerical notation? Yeah, I'm going with yes. Nobody responded because they were like, I don't know. So what is 5.9 billion? How many? So how many zeros? Million. There should be like 5, right? Ones, thousands, millions, billion. You guys agree with that? Bless you. Okay, so then my Earth, Sun to Earth, is 149,600,000. Okay, so we're just subtracting these, right? So you could do this on a calculator. That's fair. You got calculators in front of you. Might as well give this a try. 4, 0, 5, 7. Did I do that right? Okay, so here's kind of one of those things where if I was going to tell you how many kilometers are between them, I might just say they're about 5.8 billion kilometers apart. Okay, so that's a significant digit idea, right? I'm not going to say, well, it's exactly 5,750,400,000. That's ridiculous. Your brain doesn't comprehend that. If you just say 5.8 billion, that just is the same thing, right? Kilometers. Okay, how many times further away? How many times further? Okay, so if I have a small thing, what mathematical operation am I going to do if I have small, how many times bigger? I feel like this is too obvious if I say it. Small times what equals bigger? Okay, you multiply. Times, right? Times. So times some number equals the larger thing, right? Something small times the value. Okay, so if I want to figure out how much it is bigger, okay, I'm kind of solving for the x. So if you can do this in mathematical equations, I'm going to solve for x. Okay, so to figure out how much something is bigger, how many times bigger, you'll always do the larger thing over the smaller thing. Okay, so my larger number was 5 billion. So I'd take that, divide by the smaller. 149,6. You did that already? Should we all take his word for it? Okay, everybody can do that on their own, right? We don't need to practice that. 39? Was it exactly 39? 4. I'll say point times 0.4. Okay, so if we were going to write this like so, Pluto is 39.4 times further than the Earth from the Sun. Sun. Does that make sense? What you're finding there? So almost 40 times further. That's a long ways. Wow. Okay. So now we're just comparing two numbers. First of all, which one is bigger? The larger number is, I have negative exponents. So which one is larger? first one or the second one? The one with the bigger estimate, right? Okay, so -4 is larger than -7. Okay, so the larger number is 2 times 10 to the -4. Okay, second question says, how many times larger? So what am I going to do? How do I find times larger? Which one is larger? So which one goes on the top? Second one. So 2 times 10 to the -4 over 9 times 10 to the -7. Let's do this one in the calculator. Let's make sure we can type this correctly. So everybody grab a calculator in front of you. Okay, I want to make sure everybody knows where the fraction button on the calculator is. Where's the fraction button? Alpha y equals. Okay, so if you hit alpha y equals and hit enter, that's going to give you that fraction form so you don't screw this up. Okay, you got a top and bottom. Now I'm just going to type it in how I see it. 2 times 10 to the -4. And do make sure the negative button is that one. Okay, this calculator is negative and minus. Only calculator in the world. I don't know. 10 times. Oops. Did everybody get a whole bunch of 2s? 222.2. So 222.2 times larger. Would you have guessed that without doing that? We should have made guesses first. That would have been interesting. Okay, let's make a guess this time. Kilometer compared to a centimeter. Okay. Now this one you can kind of comprehend because your centimeter is like that big. Kilometer is like a mile. So what do you think? How many times bigger is the kilometer? Guesses? 100? What'd you say? 100,000 times bigger. Did you already do the problem? Oh, that was a good guess. Maybe, maybe not. I don't know. Let's find out. Let's see. Okay, so we're going to do to figure out how many times bigger something is. You got to go top bigger over smaller, right? So the kilometer is obviously bigger. Okay, so the kilometer is going to divide by the centimeter. Okay, so how many meters is a kilometer? 1,000. 1,000 meters. Okay, so how many is a centi? You're close. Okay, so remember, this is a meter right here. Centimeter is this. So it's an ith. It's an ith, right? Okay, let's go like this. Remember our little sheet up here? Centi is 10 to the -2. So 0.02. 0.01. I don't know where I got to, but there was a 2 in there. 0.01. 1 because we're talking about one thing. So, anybody want to guess what 1,000 divided by 0.01 is? That's a good guess. You said that, right? 100,000? Oh, it's a lot. So smart. Okay, 100,000 times bigger. Interesting. Okay. I kind of think I don't need to do this. Do I need to review exponential rules?